We'll now begin exploring the ideas of antiderivatives and what's called indefinite integration. Now, indefinite integration basically is the technique of finding antiderivatives, but what's most important right now is knowing what an antiderivative is. So we're going to say that a function capital F is an antiderivative of a function f, where its derivative is equal to f for all x. Now, what that really means is that we're going to work backwards. We're going to be looking at a function and ask ourselves, what do we take the derivative of that gives us that function? So for example, if I was looking at f of x equals something like, I don't know, 2x, for instance, right? Well, I would think to myself, what would I find take the derivative of to give me a result of 2x? So an answer for the antiderivative capital F could be something like x squared. And that's obviously an easy correlation here between using the power rule. But the thing is, when you find an antiderivative, it may not be the only antiderivative. It's just one of them, right? So it's not often the case that you get the antiderivative. It's one of many or an antiderivative that we're looking for. And to really illustrate my point, again, a moment ago we simply said, well, if I have something like 2x, what I take the derivative of? Well, one antiderivative, as we mentioned, was x squared. But what if we had the situation where we were finding the derivative of x squared plus 5? Well, because we're adding a constant, its derivative would be 0, and we would still end up in the same place over here. So what we have to understand is between, knowing where we came from, we always don't know whether there was a constant out there that we also differentiate to 0. So that's why it's an antiderivative and not the antiderivative. Because when you think about x squared and all the numbers you could add or subtract from x squared, they kind of create a whole family of things who all have, the same derivative, so that all of them are antiderivatives of that function. Now, in order to find antiderivatives, we do what's called indefinite integration. And this is what the notation looks like that's telling you to do that. So when you see this, it's telling you to find the antiderivative of f of x with respect to x. So this symbol right here is called the integral. And this right here is the variable that we're anti-differentiating with respect to. Similarly, when you want to find the derivative with respect to x or maybe t or whatever variable, this is that same idea. It's saying find the antiderivative of this function in terms of x, right? That's kind of the variable you're working with. Now, when you do that work, it of course equals the antiderivative. So we'll just call that capital F. But that's not enough. Remember, there's an relatively an infinite number of answers because you could add or subtract any number to it. So the way we notate that is we say plus a capital C. So this right here is the integral symbol. This right here is our variable of integration. This, of course, is the antiderivative, and this number C is called our constant of integration because we have to accept the fact there could be a number there whose derivative, of course, would be 0, giving you the same function f of x. Now, it's important to note that differentiation and integration are inverse operations, okay? So finding a derivative and finding an antiderivative really are opposites, and that's really the way you want to look at it. So in other words, if you find the derivative of finding the antiderivative, they basically cancel out, leaving you simply with f of x. Now, that's important to know because obviously moving forward, as we find antiderivatives, we don't want to generate a new long list of things to memorize, but instead, we'll use the power rule and the other sort of rules of differentiation that we already know and simply work backwards. So when you see this integration symbol right here, right, to find that indefinite integral, what you want to think to yourself is, okay, what did I find the derivative of to arrive at this? Often that's the best way to do it because, again, we don't want to have many, many more things to memorize and then maybe possibly mix up. We just want to stick with what we know, all right? We know many derivative rules, and so when we see this, we'll simply work backwards and ask ourselves, what did we differentiate to arrive here? So here's a list of the basic integration rules we want to be able to know, okay? And the ones over here on the left are mostly like the basics, some of the structure ones. Everything over here on the right kind of leans into the stuff we've talked about before with derivatives and just using those rules backwards. So over here on the left side, we talk about, for instance, 0. So you think to yourself, what do you take the derivative that gives you 0? Well, the answer here is always going to be C, because obviously the only thing whose derivative is 0 would be a constant. Now, the second one looks a little strange, and while this isn't really a big deal compared to other ones, I think it's important to write down because for some people, it messes them up. They just see this blank space and they're not sure what to do with it. But what's important to remember is that the dx isn't really just a symbol, it's really there, and it's something you can do math with. So what's written here really is 1 times dx. So when you're talking about the integral of dx, what you're really saying is, what did you take the derivative of that gave you 1? Well, the derivative that gives you 1 would be the thing x. And then, of course, as always, you write plus c. So any x plus a number's derivative would be 1. Now, as far as k being constant, what this just really means is, and this is very similar to what we did here, is that you're always going to basically have, because you have a number, be coming off a linear like this. This was the special case where k is 1, but in general, when k is really any number, that just means the derivative came from you taking k times x plus some c. Okay, and the derivative of any x by itself linear would be that coefficient. Now here, number 4, we're just going to talk about how to tackle, integrals, right, when you have two separate things maybe being added or subtracted. Well, just like limits and derivatives and everything else, you can break them up and do them separately. So here you could find the antiderivative of the first part f of x, and then either add or subtract the antiderivative of the second part g of x. And again, this should have the same exact look and feel of like when we did derivatives. Which leads me to number 5, same idea. If you're finding the antiderivative of f of x and it's being multiplied by a number, that number can basically just go along for the ride. So what you can do here is just find the antiderivative, in this case, capital F of x plus c, but that term, you can just put the k in front and multiply by that. Now, looking over here on the right, now we really more directly look at our former rules of differentiation. And again, think backwards. We look at each of these and say to ourselves, what did I take the derivative of that made me arrive at this spot? So for most of these, we really don't want to memorize them, but instead acknowledge what thing we already know can help us figure out the answer. Now, the only exception to that might be number 6, doing the power rule, only because we really want this to be an inverse operation. And so while you can sort of think backwards, this is something you actually can have an algorithm, right? A little step-by-step thing to actually make it work. So for number 6, if we want to do the power rule backwards, right, and figure out, what did we do the power rule on to arrive at this answer, what we want to do is do the exact opposite operations in the opposite order. Because again, these are inverses. So instead of taking the exponent and subtracting 1, we're going to begin by adding 1 to it. And that should feel a little different because we're going to do that first. Remember, when we found the derivative, we always multiplied, in front, and then as a last step, then we subtracted, the exponent. But because we're going to go backwards and do the opposite operations, our first step is to add 1 to the exponent. Now, after you do that, instead of multiplying by the exponent, now we take whatever that is and divide by it. And if we do it in that order, add 1 to the exponent, then divide everything by that, that is the literal opposite operations in the opposite order for doing the power rule. So this right here will tell us where we, came from that has this, this derivative. Now, as always, don't forget to write your plus c. And I do want to point out when you do this, oftentimes it's easier to think of it more as a coefficient, okay? So really what you'll often see me do is I'll have that 1 over n plus 1 in front, and then the n plus 1 right there. Okay, so while technically this is correct here in blue, usually when I do the power rule, I'll add 1 to the exponent, and then when I divide by it, I really multiply by its reciprocal in front. Power rule is always better and easier when you think of it as a number times x raised to a power, just like we did with derivatives. Now, looking at number 7, this of course is saying, what did we take the derivative of that gives us e to the x? Well, obviously that would be e to the x because it is its own derivative. So that would be its antiderivative. Now with number 8, 1 over x, you should recognize that as the derivative of the natural logarithm. But we have to be careful here. We can't simply write the natural log of x. And the reason for that is when we start with the natural log of x and we find its derivative, we already have established that it is the natural log of x and it is what it is. But when we begin with 1 over x, this x could be literally anything except 0. But when you talk about going to the natural logarithm, inside logarithms, that cannot be a negative value nor 0. So we have to put the absolute value on that to guarantee whatever this x is makes sense in the domain of the natural logarithm. So that's going to be one important little detail that we have to alter. Okay, again, we know the derivative of the natural log of x is 1 over x, but when we go backwards, we've got to put those natural logarithms in there to respect its domain. Now, trigonometrically, I really want to again emphasize not to memorize these. Instead, we really want to say, yes, I know the derivatives of the trig, so let's simply think backwards. Okay, so on number 9, if I'm saying what's the antiderivative of the cosine of x, I'm going to say to myself, what did I find the derivative of that gives me cosine of x? So in this case, it would be the positive sine of x. And that's really one of the reasons we want to be careful, because it's easy to mix up when they're positive and negative and things like that. So as long as you remember the derivative rules, simply think backwards. So again, 10's a great example. What did you take the derivative of that gives you the sine of x? Well, it wouldn't be cosine x because the derivative of cosine is negative sine x. So that means I must have found the derivative of negative cosine x plus c. And leaning on my derivative rules will help me make that correct. Now, what did I take the derivative of that gives me secant squared? Well, that would be tangent. So that antiderivative would be tangent x plus c. What did I take the derivative of for cosecant squared? Well, you should be thinking cotangent, but because this is a positive, that means I must have differentiated negative cotangent of x plus c. And the same is true for the last two, right? The secant of x is the thing we take the derivative of that gives us secant of x times tangent of x. And likewise with cosecant of x, cotangent of x, because it's positive, that means we did the opposite, right? The negative cosecant of x plus c. So let's try to use these rules in action, all right? So these next couple examples are some very basic, straightforward ones that utilize all of these ideas. So to begin with number A, we definitely have x to the fifth. That's just going to be a power rule. So when I find the antiderivative here, okay, I'm first off going to add one to the exponent, and then I'm going to divide by 6, or in other words, multiply by a 6. And as always, don't forget to write plus c. Now, because we've done our first example here, I want to pause and just say this one important thing. Whenever you find antiderivatives, especially at first when you're not used to doing it, you might not be very confident whether you got it right or wrong. It's always a very simple thing to do when you get done to check your answer. Because once you write down what you think the antiderivative is, you can simply do the power rule, right? You can find the derivative and see, does it take me right back here to where I started? So for instance, if I wasn't really feeling good about 1 6x to the 6th, well, its derivative is 6 times 1 6, which is 1, and then take 1 away, x to the 5th. So doing the power rule can really give me that confidence that, yes, I did do it right. So remember, you can always use your rules of derivatives to check your answers. Now, in the next one, we have 3 different terms. So all of them are pretty much going to be doing that power rule. So we can just do each one separately, and don't forget to write our plus c. So for our first one, x to the 3 halves, when you add 1 to the exponent, now it becomes 5 halves. Now, instead of saying divide by 5 halves, this is a really good example of why I like to write it like this, right? So instead of dividing by 5 halves, I can multiply by its reciprocal 2/5, which looks a lot cleaner. And then, of course, for 5x, we're going to just carry the 5 along. So let's begin with our x, right? We're going to add 1 to that power, so it'll be a 2. And then when I multiply by a half, since the 5 is already there, it becomes 5 halves. Now, this one we talked about earlier, when there's a 1 there, that just means the thing we took the derivative of was just x. Okay, and don't forget your plus c. Now again, if you're not feeling great, especially with the fraction stuff over here, just do the power rule, right? 5 halves times 2/5 is 1, and if you take 1 away from 5 halves, you get 3 halves. So you should feel good that we did definitely get that correct. Now on this we have a mixture of some polynomial work and trig, so we'll again just do each one separately. So for 8x to the third, we're going to add 1 to the exponent to get a 4, and then when I divide or multiply by 1/4 with the 8, we'll get a 2. And that makes sense because, of course, 4 times 2 is 8. Now we go to a 3. Now I think to myself, what did I take the derivative of to give me a positive sine x? Well, that means it must have been a negative cosine x. And always, don't forget your plus c. Now, one like this, I know we have a 4 on top and of an x, and you might have the temptation possibly to rewrite it, similar to what we did with derivatives, but instead, you want to recognize this more as 4 times, and there's a 1 over x in the integrand. I say that because we really want to highlight the idea that this is going to go to a natural log. So whenever you see a 1 over x, just leave it that way because we want to land on that natural log of x. Now, because there's a 4 there, we'll just multiply by that. So this will be 4 times the natural log of the absolute value of x plus c. Now, with our last two here, we have an exponential and yet another trig, and both of them have numbers in front. So as always, just carry them along for the ride. So for this one, we ask ourselves, what do we take the derivative of to get e to the x? Well, that's just e to the x. We'll carry the 3 along for the ride, and always write your plus c. For this one, we ask ourselves, what do we take the derivative of that gave us cosecant squared? Well, it's positive, so that must mean we have a negative in there. Let's copy the 5 along for the ride, and this, of course, would be cotangent plus c. Now, those previous rules are pretty straightforward, okay? And that was just us practicing using, our ideas of derivatives backwards. But there are many problems that, like we did when we first learned the power rule, you want to rewrite. So here are some examples of problems that still can be done using these basic rules, but based on the way they're written, you may want to rewrite them first. And just like we talked about with derivatives, you want to think of it as a number times x raised to a power. If you can make it look like that, you can always easily do the power rule. And that's true whether you're doing derivatives or even antiderivatives. So if it doesn't look like this, that's pretty much where you want to go. So in our first example, instead of looking at this as the integral of 1 over x to the third, I'm going to say this is the integral of x to the negative third. And now by rewriting it, it's a lot easier for me to see where I'm going. Okay, so my negative third, when I add 1 to it, becomes negative 2. Be careful when you add to negatives. And then, of course, if I divide by negative 2, that's the same thing as multiplying by negative 1/2. And as always, don't forget your plus c. Now on this one, it's a rational exponent, right? Because we have that radical. So we can call this 5x raised to the 1/4 power. And again, by writing it that way, it's a lot easier for me to see what I'm going to add and divide by. Okay, so when I do my power rule, if I take 1/4 and add 1, that becomes 5/4. And then if I divide by 5/4, that's the same thing as multiplying by 4 over 5. So if I take 4/5 and multiply by 5 there, it just gives me a 4. And as always, don't forget your plus c. Now for our last example, we're going to see something that we really worked on a lot with derivatives, and that is dividing by a single term. And I'm going to tell you the same thing. We're just going to divide each term by that single term at the bottom, and then we'll separately do two easy power rules. So if I take x and divide it by the square root of x, that's just subtracting exponents. So if I take 1 minus 1/2, that's going to give me x raised to the 1/2 power. And then here, if I take 1 divided by the square root of x, that just means I have really square root of x in the bottom. So that's x raised to the negative 1/2. So now that I've written it this way, it's easier for me to do my power rule. Okay, so if I take 1/2 and add 1, that becomes the 3/2 power. And if I divide by it, that's like multiplying by 2/3. Now in this next one, if I add 1 to negative 1/2, that becomes the positive 1/2. And multiplying by its reciprocal, the same as dividing, is multiplying by 2. And as always, don't forget your plus c.